Welcome to this presentation on process cost as criterion in the model-based experimental analysis for optimizing phytoextraction processes. This is actually a presentation to be held at the appropriate conference, the meeting of ProcessNet, but since the cost of that conference were too high, I record this on video and supply that on YouTube free of charge. My co-author is Jan Bernd Bohl, who did most of the work at the Technical University of Graz, and I'm affiliated with the University of Liège in Belgium. So what is the motivation for our work? Well, before that I should give perhaps a little outline. First the motivation, then the systematic approach will be explained. Optimization of process conditions is then the next step to be done. Finally, I will introduce you to model-based experimental analysis and show how this can be applied also in the context of cost optimization. And finally, I will summarize the results in one slide. So what is now the motivation? Well, if you want to do plant material extraction, the question is how to approach that. And the problem with plant material is that the quality, meaning the concentration, the structure of the plant material very strongly depends on some given properties of the weather, for example, of the harvesting period, or where the plant is coming from. If it's from Asia, from Africa, from Europe, wherever. If you have plants that grow in different locations, they will have different concentrations of your desired components as well as different plant structure. And of course the structure will then influence also the speed of the extraction, the kinetics of the extraction. So actually what you would like to have is a way to design your extraction process as to account also for the differences in these different, given boundary conditions of your plant material. So in the end you would like to have a method to characterize your plant material as you receive it and use that in order to do some experiment, for example, some simple experiment, and deduce from this simple experiment the parameters of the process at which you want to run it under optimal conditions. So solvent to solids ratio, for example, the duration of the extraction, you would like to optimize these things based on a simple experiment. Okay, for that and for the design of extraction processes in general, until now you have more or less empirical process design methods, mostly building on very simple beaker experiments where you qualitatively or semi-quantitatively characterize the extraction kinetics, and from that you do then the scale up, so to speak, to large scale. The idea is to come up with a new systematic approach which uses systematic experiments in order to be able to optimize the process. And what do I mean by optimization? Well, you have various variables that you can change. For example, you can change the pretreatment method. And from a previous previous project, I can show you some effects that we have investigated in the past, and this is actually one concentrated result file. What is shown here are different pretreatment method, microwave pretreatment, drying at 105 degrees C, ultrasonication actually during the extraction process, and then different milling methods, impact mill, cone crusher, impact mill with a given diameter of the particles, then sieving, dry ice milling, because as you mill you have an energy input to your system, so the temperature will rise, and that can of course influence your the material properties and then later on the extraction processes. So dry ice milling, keeping the temperature cold, so you add to the material you want to mill, you add your dry ice, and by that you keep the temperature low. Then the impact mill, which is actually our reference state, heating and some other milling possibilities, different diameters especially. And this has been tried on different plant material, on valerian, lemon balm and pepper, and it has been investigated if the concentration that you can reach with your extraction process is increased or decreased with respect to the reference case, and if the kinetics of the extraction is getting faster or slower with respect to the reference case. And this then has been evaluated, how much it got better or got worse. And there you see that the different possibilities for the three different plant materials give different results. You see a very characteristic red and green regions. Red means it got significantly worse. Green means it got significantly better. And white means it didn't change so much, a little bit possibly, but not dramatically. And then the values have been added up, so each point has given an individual value. They have been added up, and then the different options are now ranked in a certain way. So if you want to do very efficient plant material, you might have the idea to use microwave, because in the most cases it increases the concentration of the transfer component you want to reach, that you can reach by the extraction process, and it increases the efficiency overall. Of course, you see here for the lemon balm, the amount to be extracted, which is characterized by this concentration, the starting concentration of the transfer component, is actually reduced. So you have to check for every individual application if these pretreatment methods really improve the process. But overall, this is a good idea. So you might come up with the idea to use microwave as an enhancement for the phyto extraction. Okay, so this is the basis, so to speak, and we will discuss microwave later, and you now know why microwave may be a good idea to talk about. Now, the idea of our work is to come up with a small, standardized lab equipment that allows to quantitatively characterize the kinetics in this simple model here, an effective diffusion coefficient, and the concentration that you can reach by your extraction process. Okay, so these two parameters can be characterized, and even more if you so desire. How does that simple equipment look like? Well, it depicts more or less what you have in technical extraction processes. You have two different principal types of extractors, a percolation extractor and an immersion extractor. Immersion extractor means that the plant material is mixed with the extracting solvent, in a stirred vessel, for example, whereas percolation means that you have your solid, your plant material, resting some way in your equipment, and then there are different options. You can either really have the extractant running through it with a large flow rate, or you can have it dripping, so to speak, through the fixed bed of your plant material. That is the percolation extractor. And in our lab experiments, this has exactly been depicted. So we have this in a small stirred vessel and a tube in which you can place your plant material, and now these are connected, of course, to the outside world. There's a pump pumping the extractant through these extractors, and we have a thermostat, and everything is within a thermostated bath, so that the temperature is constant. We have the ability to steer over here, and of course then also we can withdraw samples, either continuously running it through a UV-Vis spectrometer, or choose certain times where you can withdraw samples with a syringe, for example, and analyze that with HPLC, just as a typical example again. Okay, so our idea is to perform the experiments with this type of experiment, either immersion or percolation extraction, and then deduce the parameters for the extraction kinetics from that. This has been actually worked out, and I will show you now just in a moment the method that we use to improve the experimental quality, but I don't tell too much about the details because that has been worked out already in the past. That's also published, so I don't have to dwell on that too much. The new idea is now that actually we are not only interested in the kinetics. I mean, the kinetics is nice, Yeah? If it's fast, you get some qualitative information, but actually what you're interested in is if you perform these experiments to do a design of an equipment and you want to optimize the production costs reached with that equipment. Now cost, so I have to tell something about the cost model that we are using. It's a rather simple cost model. It sums up the fixed costs and the variable costs being for especially the amount of solvent or the amount of plant material that we use. And the fixed cost is mostly dependent on the size of the equipment, for example. You can, of course, do much more detail here and calculate energies that you use for pumping, for whatever, for heating and everything. This is evaluated with respect to the flow rate of our product. Yeah? Now it depends, of course, which product you choose. Is it the extract itself, or is it the pure component you obtain after a further downstream process, for example? You can decide, of course, in principle, but the things look like this. You have on the one hand side the fixed cost as a function, for example, plotted here as a function of extraction time. Because if you want to have a certain amount or production rate of your plant, of your extract or your plant extract, and you have longer extraction times, you need bigger and bigger pieces of equipment. And this, of course, means that your fixed costs are increasing as the extraction time for a single batch will increase. The variable costs drop from some value to more or less horizontal curve, because as extraction proceeds, the amount of solvent that takes this amount, that dissolves your desired component, is more or less becoming a constant because you have reached maximum concentration, so this is horizontal in the end. If you add these two values, you wind up with a curve, which is of course well known in chemical engineering. It mostly looks like that for most of the processes. If you plot costs versus some relevant parameter, that you get a cost minimum somewhere, and you are happy because, like always, if you look for a minimum, the tangent is horizontal, meaning that if you are a little bit to the right or the left, usually not too much happens. Okay, so you find your optimum, and the question is now, of course, in the end, if you want to find this optimum for a given plant material extraction, how to perform the experiments in order to be able to find the optimal condition, the optimal process with a minimum amount of experimental effort. So you want to minimize the cost, and you want then in the end to determine the parameters such that you get the experimental conditions such that you get with minimal effort also these minimal costs. Here one has to very carefully distinguish between the parameters that we are using. We are talking on the one hand side of the technical process, where we have costs of the process, cost of the product in the end. Where we also have optimal conditions, for example, an optimal extraction time. On the other hand side, we have the experiments that we perform in order to characterize the material and the extraction process in principle. And of course, there also extraction time can be a parameter. So if we want to determine, or if we talk about extraction time, we have to be careful. Do we mean the optimum extraction time or the extraction time in the process, or do we mean that in the experiment? Of course, we have taken care of that, and in the end we ask for the best extraction time in our experiment in order to obtain the design of the equipment at optimal conditions, meaning that we also optimize extraction time in the technical process. So both parameters enter in our final evaluation. Now to show a little bit how this looks like, here the specific costs are shown in euro per kilogram of rosmarinic acid. It's a pure component, and as a pure component it's rather expensive, some 100,000 euro per kilogram, as a function of the duration of the extraction of the technical process. And here you see now an example. These experiments have been performed, and it has been estimated how expensive will the product be in the end. And from that then the following things more or less evolve. On the one hand side you have your reference. That means also the reference that I have shown before in this slide with the different options for the pretreatment, you get, as a function of extraction, technical extraction, you get a certain cost function. If you now account for the microwave, that is that you perform microwave treatment before you extract, and this is really taking place before, then you see that if you just use the same cost function as before, you get better. The costs are decreasing, not much, but a little bit. Now, of course, you have to take into account that the microwave energy will also generate costs. And this means that you have to add them, and if you do that, you wind up with the blue curve. So red is without taking the microwave costs into account, and the blue is with taking that into account. And you see, of course, that the things increase, but nevertheless, the minimum here for the blue curve is less than the minimum of the black curve, and it is located at a different time. Yeah, so you would like to know this influence, of course, and you would like to quantify that and be able to find your optimal condition, so to speak. Okay, so this is the background of experiments that we have performed, and based on these experiments we now try to find the optimal experimental conditions to perform the optimal experiment, the optimal design of the technical process. So now we are doing this, what we call model-based experimental analysis, that you also find in the title of this presentation. It's abbreviated as MEXA, and it's a one way of planning your experiments in the optimum way. I show you here the mathematical background. We use the Fisher information matrix, which is specified by this mathematical expression, and this characterizes the information obtained from an experiment, and we maximize some measure of that information, and as a measure we use the determinant of the Fisher matrix. One can use other options, but it's not the place to discuss that in detail. Now, what is the V and what is the Q? Actually, it's specified down here. On the one hand side, the V is the covariance matrix of the experimental errors, and if you have independent experiments, you only have diagonal values, that is, the individual variations or uncertainties of each experiment. That depends, of course, on the concentration, for example, because GC, HPLC, or whatever has specific error functions, and depending on the concentration, you get a certain plus-minus deviation, and this is characterized by this covariance. If you have experimental data where the data depend on each other, or there is a certain dependence on each other, for example, because it's a time series, and of course an error in one experiment can propagate to the next experimental value, so that has an error as well, depending on the error of the first one, then the non-diagonal values here also may take non-zero values. You have to quantify that, of course. Thinking about these uncertainties helps actually already to get some information about where to perform experiments optimally. And then we have this Q matrix, the so-called draft matrix, which is the answer of the experiment, which is the Y. So Y is our experimental value, as a function of the model parameters. So we ask for the derivative of the outcome of the experiment with respect to the model parameters. We have several model parameters possible, and in this example, well, the J also has an index. You can also account for a variety of experimental results. If you only want to know the concentration in extraction, for example, then that is your experimental value. So the concentration you have obtained, for example, is the Y, and the diffusion coefficient and the starting concentration in the plant material may be our parameters. So this dimension is the parameters, and you write it down for every measuring point. Actually, you know only n-1 experimental points, so you have performed a certain number of experiments. And since now these derivatives depend on the conditions of the experiment, duration of the experiment, solvent to solids ratio, they have specific values, all these derivatives. Of course, you need a model for that. So you have to assume at least a certain valid model that describes in principle what you are doing, what the experimental outcome is. And then you ask yourself, well, how do I have to perform my next experiment, experiment N, at which conditions? And these conditions again define these derivatives, and then you can plug all this into this equation so that the F is maximized, so that the Fisher information, or that the information is maximized, and the information actually described as a determinant of the Fisher matrix. So that way you are able to ask, where should I perform my next experiments to get the best out of this experiment? And to show a little bit how this works, we have presented here a very simple example. The model is y is a times x. X is the experimental condition, A is some coefficient, some parameter, is a theta, so to speak, and the Y is the experimental outcome. And if you plot this curve for a variety of options, A1, A2, A3 as parameter, you see that possibly performing your experiment at x equals 0 will not generate too much information. Because if this is the correct model, you don't get any information if you perform your experiment at x equals 0. Okay. So you want to perform your experiment at non-zero values of x. And now you can evaluate the equation I've shown before, the Fisher information matrix, determine then the determinant of that. And what you wind up is, if you evaluate it like that, it's an x over sigma squared. That is, you take, on the one hand side, the derivative of the outcome with respect to the parameters. And of course, if that is getting high, it means that your experimental outcome is sensitive to changes in the parameter. And of course, exactly where you maximize that, you get the most information out of the experiment, always relative to the experimental error. And in this case, it looks like that. It's a parabola, so that which means that you increase your x, you quadratically increase the information you get out of the experiment. Of course, in this simple example, everything is easy and simple, no problem. But if you look at that in a little bit more complex situations, you will not be able to see directly where the optimal conditions are. So it's simple to see how it works for the simple case. So that's why we have prepared that. On the other hand side, if it's getting more complex, you really don't know. If you now perform this for our photo extraction process and model that with a model which is shown here, you see the concentration, some experimental data points, and you see the model that runs through that, this blue curve. It's a simple diffusion model. Then you see it fits more or less. You see certain deviations here in the end. Here there's one region which is very well described, another region which is very well described, and the zero is of course proper as well. And now if you evaluate the Fisher information, you obtain a curve, a red curve, which is shown here. And you see that there are more or less two regions where you should perform your experiments. That's what the curve tells you. You should perform experiments over here because there you have the maximum information, and also at these regions with respect, as before, function of extraction time. And the point simply is that if you perform the extraction, which proceeds like this, you extract more and more as time proceeds, in this region the slope is very high, and the slope of the extraction curve corresponds or tells you something about the kinetics. That is the diffusion coefficient of the model, which you characterize here with a high accuracy. On the other hand side, at high extraction times, you approach more or less equilibrium, and this tells you something about the maximum amount of your transfer component that you can extract. So these two maxima are directly related to the parameters of the model. You have two parameters, and then you usually get two maximum values which correlate with the parameters in this simple case at least. Okay, so far so good. We have our experiments, we have our MAXA, or model-based experimental analysis, in order to optimize the conditions of the experiments to get maximum information on the parameters of our model, and everything is fine. But now actually we set out to determine something different. We actually wanted to determine cost, didn't we? And so what we have done so far is find optimal experiments to determine the model parameters. But who actually is interested in model parameters? an engineer is looking for costs. So you want to perform your optimal process design and you want to optimize with respect to cost. So you have somehow to introduce the cost into this scheme. So what is actually desired is the optimal experiments for minimizing the costs at optimal process conditions. And there you see you have your optimal experimental conditions to determine the optimal process conditions with respect, and optimal process conditions meaning with respect to the cost that you generate. Now, in order to be able to do that, you have to do some math again. How does it work? First, a little bit text, and then we have some equations. So you want the cost minimum for the optimal process conditions. And you, in order to describe that, you also have to say something about the accuracy of the costs. And that is influenced by, of course, the accuracy of the extraction model parameters, again, and the experimental conditions. And what I stressed already is that you have different conditions. On the one hand side, the optimal experimental conditions and the optimal process conditions. One has to keep that apart and not mix that up. That took quite some time actually to work that out. But once you had the nomenclature right, it was more or less straightforward. So the question is, how do the experimental conditions influence the accuracy of the cost minimum? And in order to do that, you have to say something about the uncertainty of the cost, and you can determine that with the propagation of uncertainty with this fancy equation. You can evaluate that, and here you directly see the different influences on the one hand side of the experimental conditions, where the parameters are determined, so to speak, the uncertainty in the experiment, and vice versa. I mean, you fit your parameters to the experiment and they contain the uncertainties, so they generate also uncertainties in the parameters. And on the other hand side, you have your optimal process conditions, where you minimize your cost with respect to the parameters. If you put these together, you wind up with this equation. If you plug this now into this model-based experimental analysis scheme, the experimental planning scheme, you wind up with certain results. And if that approach makes sense, there is a difference, of course, if you do it conventionally as before, if you include the costs. And that is what I want to show here. Shown is now that we want to perform an experiment, and we ask ourselves, at which time should we perform our sampling? Withdraw a sample in order to then analyze it by HPLC, for example. So where do we get the most information out of it? And there are two things that we want to do. On the one hand side, we have the Fisher information matrix. The determinant of that with respect to the maximums is all normalized to unity. And you see that the information is, as I said, somewhere high up here and somewhere high up here. I discussed that. This is more or less a diffusion coefficient. This is the overall concentration of the transfer component in the solid that is characterized by this maxima. So here you get the concentration accurate. Here you get your diffusion coefficient accurate. In between, you don't know, you don't get too much information of either of these values. Now, if you on the other hand side look at the error for the cost minimum, you get this blue curve, and you see you want to minimize that error, of course. Now it's switched. So you want to minimize the error. What you see is that you get a minimum over here, a maximum there, and a minimum also here. So here you just do it for long experimental times, and you will get your concentrations more or less right. But here there's already a significant difference. Where should you perform your experiments? Well, the difference is not that complex, not so much in this simple experiment, but of course, as situations get more complex, you don't see actually how that moves, and the changes may be quite more significant. You see that optimizing the conditions for exact statements on the cost of the optimized process in the end are at different sampling times as those for determining the model parameters. And that distinction is important in that point. And if you look at the quality, you see here that you lose quite some % of your accuracy. Here it's not too much, as I said, but of course, as things become a little bit more tricky, that can be increasing significantly. And it's important for us to show that you perhaps should not look only at the parameters, but actually at the cost of the process. And you can do so, and why shouldn't you if the math works out quite nicely. So with that, I would like to summarize. I've shown this new systematic approach to perform experiments, to determine the model parameters from that with model-based experimental analysis. I have shown how we characterize the scale-up and account for the cost, especially for cost minimization, and how that works and how that is dealt with. Then I have shown a little bit about the optimal process conditions and pretreatment methods to gain optimal costs, minimal costs. I've shown the different pretreatment method, and microwave was one option for that, and that we have looked at a little bit later as an example. And we saw that maximizing the information with respect to the cost minimum changes the answer of the system where you should perform your optimal experiments in order to get the maximum of information. Not on the parameters now, but actually for the cost. And that was the result of this research. So I would like to thank you very much and have fun using this. Bye-bye.